The question is, could you discuss methods for analyzing a statically indeterminate cylindrical shaft subjected to torsion? So this is the sort of problem we are talking about. In this example, I have a solid cylindrical shaft consisting of 3 segments, each with different radius and different lengths. The shaft is subjected to 2 internal concentrated torques, one at point B and another at point C. The shaft is fixed at point A and point D. In this example, the shear modulus is constant throughout, but in general, even that could vary from segment to segment. So why is this a statically indeterminate problem? So how do we answer that question? The first thing we do is we cut out the shaft out of the supports and complete the free body diagram by marking the support reactions, right? So there is a fixed support at point A, and therefore there's going to be a torque at point A. Let's call that as TA. There's a fixed support at point D. There's going to be a torque at point D. Let's call that as T sub D. And therefore, there are a total of 2 unknowns in this problem. Only equilibrium equation we can write down for this is a torque equilibrium equation for the shaft. So that will be this right here. So here what I'm doing is I'm summing up the torques acting on the shaft in the counterclockwise direction and setting that to 0. So TA goes in the clockwise direction, TD goes in the clockwise direction, 8 kilonewton goes in the clockwise direction. So these 3 will go in the equilibrium equation as negative term, and 50 kilonewton meter acts in the counterclockwise direction. So that goes in as a positive term in that equation, and set the sum to 0. So this is our equilibrium equation. Therefore, the number of equilibrium equations that we can write down for this problem is actually just 1. Therefore, Nu is greater than Ne. By definition, this is a statically indeterminate problem. We need 1 additional equation to solve for the 2 unknowns, T sub A and T sub D. Then, of course, we can calculate everything else, including stresses in the different segments, angle of twist at the interior points B and C, and so on, right? The second equation we need here comes from what is called the displacement compatibility. We know there are 2 fixed supports, right? Support at point A and support at point D. Let's say we go ahead and write down an expression for the angle of twist of point D with respect to point A. What should that be? That should be equal to 0 because point D is fixed, right? So this is the displacement compatibility equation. This furnishes the second equation we need to solve this problem. But if you recall, just as in the case of the statically indeterminate axially loaded problems, there are 2 ways to go from here. In other words, there are 2 ways to calculate the angular twist of point D with respect to point A. In the first method, we take the support reaction at point D and treat that as an external force along with these other forces. Then we can come up with an expression for the angle of twist at point D with respect to point A, and we set that to 0. So in that equation, there's going to be 1 unknown, which will be T sub D, and then we can solve for T sub D. In the second method, we take this problem and split this up into 2 problems. In the first problem, we simply have these external forces, right? 15 kilonewton meter and 8 kilonewton meter. In the second problem, we simply have this external force T sub D. We come up with the expression once again for the angular twist of point D with respect to point A for these 2 problems, and combine the 2 in order to come up with the net angular twist of point D with respect to point A. The basis for this approach is the principle of superposition, right? So once we come up with the expression for the combined angular twist of point D with respect to point A, we set that to 0. Both of these approaches lead to the same final set of equations and therefore the same results. And in the subsequent slides, I'm going to use this first approach. Let's recall the formula for the angle of twist from our theory video. If we have a simple single segmented shaft like this, subjected to a torque at point B and fixed at point A, then the angle of twist of point B with respect to point A is given by this expression, right? TL over GJ. T is the torque, L is the length, G is the shear modulus, J is the polar moment of inertia. Just to simplify the notations a little bit, let's go ahead and define these coefficients like it's done here. Little f AB equals L over GJ evaluated for the segment AB, and FBC is similarly defined, FCD is similarly defined. Now on the basis of this, the angle of twist for segment AB is FAB times TAB, where TAB is the internal torque in segment AB. Similarly, phi BC is FBC times TBC, and phi CD is FCD times TCD. Then to evaluate the angle of twist of point D with respect to point A that we need in this displacement compatibility equation, all we have to do is to sum up these three quantities algebraically. That's it. Summing up algebraically implies we need to have a sign convention. Just to summarize the method, there are two unknowns, TA and TD. The equilibrium condition gives us one of the two equations needed. The displacement compatibility gives us the other equation. So using the two equations, we can solve for these two unknowns first, T sub A and T sub D. Then we use the torsion formula to calculate the stresses in each of the three segments. And these are those formulas. And here TAB, TBC, and TCD are the internal torques in these three segments respectively. Rho is the radius starting from the center, measured from the center. JAB, JBC, and JCD are the polar moment of inertias of the three segments. And of course, if you are interested in calculating the maximum stresses, shear stresses in each of the segments, we will be using the radius of the shafts for rho. Now to calculate the angle of twist of the interior points B and C, we first go ahead and calculate these coefficients, which are, by the way, called flexibility coefficients. And then we calculate the angle of twist for each of the segments, A, B, B, C, and CD, and then sum them up algebraically in order to find the angle of twist for the interior points B and C. Angle of twist of B with respect to A would be simply the angle of twist of segment AB. Angle of twist of point C with respect to A would be angle of twist of the segment AB plus the angle of twist of segment BC. That's it. So this is how we solve a statically indeterminate segmented shaft subjected to interior torques. In fact, you may note that if this is all we want to do, we don't even need to calculate values for FCD and PCD. But having values for these quantities would allow you to check your answers. Say I continue to go ahead and calculate the angle of twist of point D with respect to point A by this equation. What should that be? That should be 0, right? So if I get a 0, I know I have done the calculations correct up to this point.